Okay, welcome to the next video in the systems programming video series. We are now done with reading chapter 13, and we skipped section 13.3. So now I think we are on to doing this jam number 4. So in this jam, we are going to answer, how is machine code generated from the source code? What is the relationship between machine code and assembly? So we've been through this a couple times, but source code gets pre-processed maybe if we want to really talk about a bunch of the steps in between, which shouldn't really be the point, so maybe we won't talk too much about that. But source code goes through maybe a little bit of pre-processing, but then it gets ultimately turned into assembly code. Assembly, we've seen once before, is somewhat readable, although less readable than source code, C code. But then assembly gets turned into machine code. And this is not in a way that is easily reversed, but I don't know. Maybe I'm rambling by the time I say that, so I should catch myself early and not ramble too much. So how is machine code generated from source code? I'm not totally sure I know exactly what they want to hear in response to this, but I guess it's essentially that the source code gets turned into assembly and assembly gets turned into machine code. So what is the relationship between machine and assembly? So machine gets directly turned into, or assembly gets directly turned into machine code in an almost kind of one-for-one way that a particular block of assembly gets turned into machine code in a pretty simple and direct relationship, I guess is what I want to say. So anyway, okay, on to number 2. What is a register? A register is essentially just small, fast storage that is right on the CPU. Okay, moving along. So what 2 steps occur when the CPU executes the instruction push %RBP? And we've seen that before. I could go back and look at exactly how it's written, but I'm just going to state the high-level description. And the high-level description is that we decrement the stack pointer. So keep in mind what that means is that we go up in the stack, or at least the region of memory reserved for the stack. And so we decrement it, meaning we go up to a lower address, and then we store the new data at that new lower address. So we would store whatever the current base pointer is in that location. That's essentially what push does. And so what I am saying that there is both a command that changes the stack pointer and also a command that copies over the base pointer, right? So those are the 2 steps, right? The shift in the stack pointer and the moving the base pointer into the new location of the stack pointer. That's a high level description of the 2 steps that occur. Okay, so then the 2 steps that occur during a pop is that the data that is at the current location for the stack pointer gets moved into this destination. This is now a destination, whereas here this was a source. So data gets moved into the base pointer, and then the stack pointer gets incremented to move down in the stack memory locations. Okay, what does call Q do? So call Q will push the return instruction pointer onto the stack. So to emphasize the point, it starts with a push command, and in particular, it takes the instruction pointer, right? Recall the instruction pointer is the thing that tells the computer, the CPU, what the current instruction is that it ought to be executing. So it pushes that onto the stack, and it will set the instruction pointer to that of the called function, right? So this is always being used when you call some function. Why is it doing that? Maybe just the high-level description is somewhat more useful at the current moment because we've already seen the low-level description, and you can always go back and look at that. But at a high level, what's important to understand is that we save the current instruction pointer so that we can come back to it when the call to the function has finished. So we save that, that's the push to the stack, and then we load in the called function's instruction pointer so that we start executing the called function. So that's the high level description. Okay, let's move on to question 2. So consider the following code segment. So this is a bunch of assembly code, and we imagine that the address, oh, I see, I see. So there is like some address in memory, which I guess we're going to say the address is this, and the value of it is this string. The string holds the characters %d space %d and uh, null character to terminate the string. I assume. Actually, it may not even be all that important whether or not it actually contains the null character. So I'm not sure if we need to assume it, but probably it doesn't matter either way. But I guess we're about to find out. Okay, and then we imagine that the registers have all of these given initial values, and this assembly code starts running. What is the value of OX, so that's hex, 10 as a base 10 integer? Well, that is basically just a 1 as a coefficient to the 16 to the 1 term, I think I should say. And so effectively, that just means that this is the number 16. What is the value of this as a base 10 signed integer? So it is signed. So I think maybe the way that I want to think about what this is to imagine that you start at 0, right, which we know to be just all a bunch of hex 0 characters. And then if you went one step to the left, we know that would be -1, what we understand to be -1, but in hex, that would be, first of all, Fs, as we have somewhat described. I think I've basically made this point that if you have any base system and you're at 0, so in any base, 0 is always represented as a sequence of all zeros for however many symbols you have. And then when you go 1 to the left of that, you would get all of your largest possible digits. It would be a sequence of all your largest possible digits when working in 2's complement. So if this was like a binary number, then from 0 you move to the left and you would get a sequence of all 1s. Well, if we're in hex, it's the same idea, except that now we're getting a sequence of all Fs. If this 7 were an F, is essentially what I'm getting at, then this would be the number -1. But it's not F, it's 7. And so we can go back and back toward further and further to the left. Or maybe the easiest way to think about this is just this is a smaller number than -1, right? Because if that was an F, it would be -1, but we need to go to the left of that because it's smaller. And then I guess we want to know how far to the left do we want to go? And that's essentially just the same question as how many numbers are there between 7 and F in hex. So if we took 7 plus 3, that would get us A, because A is 10. So that's a difference of 3 getting you to A. And then another 5 digits, I guess we could say. Is digit the right word? Hex digits, maybe? In any case, you go another 5 to get all the way to F. 5 and 3 is 8. And so that would get you to -1. So essentially what I guess I'm trying to get at is that this thing must be 9 steps to the left of 0. That is to say, this thing is -9. Right, because if you took one step to the left, that would be -1, and that would be all Fs. Do another 8, and you get down to a 7 character here. And so, end of the day, this is the same as -9. This is a pretty long problem, so maybe to not make this a long video, perhaps I'll end it here, especially because now we're just starting to get into tracing through the register values and stuff after certain code executes. So maybe we'll start that in the next video.